All right then, this is Aryan. I just decided I would make a video like this in this Walmart-esque Salcon setup. I wanted to make a video like this because I was feeling super studious. I had a couple of loose pieces of info in my head, and I wanted to essentially reinforce them. And what better way to reinforce them than to teach you um, basically one of the concepts that I have tried learning a bit, and I think I've gotten to the point where it's deep enough in my understanding to help you understand it just a bit better. So today, the concept we'll be covering is called atmospheric retention, and it sounds obscure. It sounds like one of those things you would talk about in university that you never actually get to use in your life. But this is really useful. It says ATM retention here, but it's really atmospheric retention. Just a quick disclaimer. All right. So what this concept does is it tries to answer the question of why do certain planets and celestial bodies have atmospheres, if they do, right? And if they do have atmospheres, what are those atmospheres going to be composed of in terms of the elements, right? So if you look at Earth, we actually have a really interesting atmosphere. We have 72% nitrogen in our atmosphere. And actually, most people who are watching this video, you might not know that. 72% nitrogen. How do you breathe? Well, 21% oxygen. All right, and everything else just kind of falls in line from there. We have trace amounts of argon, so that's a noble gas. And we also have CO2, which is like 0.00, some small number, right? But it is going up, of course, because of global warming. 72% nitrogen, 21% oxygen. Now, what is the math that describes why Earth is structured this way, at least in terms of its atmosphere? Well, the way we can look at this is, I mean, let's not mess around. Let's get into some rocket science. Very simple rocket science, though. So what we have here is a formula for escape velocity, and I'll tell you why this is important. The main reason why certain planets, etc., have certain atmospheres, if they have atmospheres at all, has to do with the simple question of what is this planet's escape velocity, which is what I've said here, VE. What is this planet's escape velocity versus the speed of certain gas molecules, right? And gas molecules make up the atmosphere. And depending on how easy or hard it is for them to escape a planet's gravitational field, that's going to really change what the atmosphere is going to be made out of. So what we're going to do as we go on is plug some numbers into here and see where we can get in terms of a theoretical mathematical calculation for our atmosphere. So I really briefly touched on what VE was. It's escape velocity. So how fast anything needs to go, regardless of its size, as long as you're in a certain planet, how fast it needs to go to escape. Sorry, wow, my English is messed up. To escape that planet's gravitational field. So think about a rocket, think about an atom, whatever, right? And this formula is really simple. Everything's under a square root. You just really need some grade 8 arithmetic to figure this out. 2 is a constant right here. It's, we just need it to make the equation work out well. G is this thing called the gravitational constant. It's also another constant. Wow, my handwriting also sucks. Wow, I might just, become a doctor too while I'm at it. 2 is a constant. G is a gravitational constant of any planet on its surface. And R is, probably heard of it, it's the radius. Okay, maybe you've used this when you're finding the area of the circle, for example, with pi r squared. The reason we just assumed it's a radius and we've assumed this is, well, specifically a sphere when it comes to planets is because in space, things are really sizable. And they eventually just compact themselves down into spheres. And that's what we see with all these celestial bodies. So we just put that assumption in there and we're correct like 100% of the time because things are just so huge in space. So what do we do with this? Let's actually try plugging some numbers into here and seeing what we get. 2 is going to stay the same. Gravitational constant, you might have seen this number too. It's 9.8. 9.8 what? 9.8 meters per second squared. So this is the acceleration of any object that you could, let's say, drop from your hand, assuming you don't put any other extra force into it. This is the speed that the object takes, well, not the speed, the acceleration, right? How fast the speed increases as it falls to the ground. And that's Earth's gravitational constant. Next, we multiply that by the radius. What's the radius? Specifically right now, the radius is going to be 6.4 million. Okay, now that's probably a bigger number than you've seen in most formulas. And really, this number is supposed to be 6,370 kilometers because that's the radius of the Earth. The thing is, acceleration's in meters right now, so we're just gonna convert 6,370 kilometers to meters, and that's what we get, 6.4 million meters. So 9.8 times, 6.4 million, that's an obscenely huge number. It's like 80 million or something like that. That's my estimate. Times it by 2, and then you find the square root, and I did the math earlier, and VE is equal to 11,000 meters per second. So for context, that's how fast something would need to travel consistently to escape the Earth's atmosphere at the very, very least. All right, this is just to match the escape velocity, right? If you want to go into space, you need to go faster than that. So that's how fast rockets need to go, by the way. But specifically for our example, we're going to span outside of rockets and see some more far-stretching examples of how escape velocity can be used. Okay, so now that we've teleported to a blank page, let me just tell you that that was half of the story. Escape velocity is half of the story. The second half of the story is, well, how fast certain atoms and molecules move, and that dictates a lot of things. So let me show you a new formula. It's also a V, but here it's V mole. And V mole is described by another square root, very common, both of these, equations. A lot of equations about speed tend to have square roots in them. This equation is described by what we call 3R with a little bar on top of it, 3RT over, and I'm pretty sure that's correct. Wow, that's a really long, let me just erase that. Okay, cool. So now that I've fulfilled the needs of my OCD, let's move on. 3 is a constant, right? Just like pi, whatever. It makes the equation work out. R, I'll actually get to R. Let me explain the other ones. T is, of course, temperature. Actually, it's probably not, of course, temperature. There's like a new equation I'm introducing it to you. Temperature, but specifically in a unit called Kelvin, right? Just like degrees Celsius, very easy conversion. Whatever you have in degrees Celsius is, well, let me just do it here. Degrees Kelvin is equal to Celsius plus 273 degrees, right? So if you have like 10 degrees Celsius, it's 283 Kelvin. Whatever, 1 degree Celsius is 274 Kelvin. You get the gist of it, right? And M is a specific unit we call molecular mass. And this, okay, molecular mass. And you see, the thing with molecular mass is I mean, you've probably even heard about it in high school. It's just another unit of weight, right? And with all of these things combined, we'll be able to find the average speed of a certain molecule or a certain atom, right? Depending on what we're looking at. And back to R, good thing I didn't miss it. Wow, I'm just doing this really messily. Hopefully you guys can understand this still. R, what R is, it's another constant as well. And if you're wondering why I didn't write it out as a number, R is equal to 8,314. But what is the unit of 8,314? Well, it's this. Okay. So 8,314 joules, which is a unit of energy, kilomoles, which is a number of atoms, and Kelvin, right, which is a temperature. And what R does is it serves two main purposes. You don't need to confuse yourself too much about R. We just use it. Is it takes, number one, all of these disparate units, so temperature in Kelvin, we're looking at, molecular mass. That's, analogous to any unit in weight that we could look at. So right now it's molecular mass. It could be kilos, grams, whatever. You can't really compare those, right? So what we're doing partially with R is we're using this as a way to compare all of these units and get a very nice clean answer. Without R, we'd have shambles as an answer. All right. That's part of the function. Second, this 8314 part of R, if you just ignore the units for a second, it helps us describe just how air would behave. This is R is also known as the universal gas constant. It's a very popular scientific constant, akin to pi in a way, right? And it describes the natural way air behaves in ideal conditions, right? So nothing too extreme, and it's more or less what we need to describe how things will behave in Earth. So if we were to plug something into this, what would we get? Anyone know? Well, yeah, because you wouldn't know because we don't know the molecular mass of anything right now. And that's exactly what we're going to get into. Well, now that we've teleported again to a new screen that is probably really confusing right now, let me try explaining this better. If we try just traveling back to our equation for molecular velocity, what we end up seeing is that imagine if you were comparing two different gases, right? They're two completely different elements. They compose two completely different molecules. 3 and R, they're going to stay the same regardless of whatever you do, right? And if you're just trying to compare two gases and you want to keep all the other variables controlled, you're assuming the temperature is going to stay the same too. So the only thing you can change, the only lever you can pull when you get a new gas is a new molecular mass, all right? And to give you better insight into that, this is exactly why I've drawn a little table of molecular masses of common elements. So hydrogen is actually the most common element in the universe. And this isn't just any kind of hydrogen though. If you're a chemistry whiz, you'll see that this 2 means something very special. This isn't regular hydrogen. This is a type of hydrogen called diatomic hydrogen. Let's see if I can write this in time. Diatomic hydrogen. So di meaning two, it's just two hydrogen atoms bonded together, right? And as a result, since each hydrogen atom has a molecular mass of 1, again, the molecular mass of something is you just add the number of protons and neutrons in an atom, each being 1, right? So hydrogen is just 1 on its own because it just has 1 proton and no neutrons. You don't count the electrons, by the way, they're super light. It has 1 neutron alone, but since there's 2 of it, and you can register that as 2 different molecules, that's a molecular weight of 2. Cool? Well, let's try scrolling down to more, how would I put it? Atmospherically significant gases. So as you go on to helium, helium's still really not very abundant in our atmosphere. It has a molecular weight of 4. And you'll see that as you go down the periodic table further and further, these weights are going to increase. Well, I'd like to be more exact. They're masses, right? So N2 is also diatomic. Anything with a 2 on it is really diatomic. If you go back to the H2 thing, you've definitely seen that before, H2O, right? It's not just HO. These things like to bind together. They have an affinity for themselves. And N2 is no exception, right? N2 is just, 14 here, 14 here, and that gives you 28. That's a slightly heavier one, but there's certainly much, much more heavier ones. I won't get into those right now, but N2 and oxygen, they're what really matter for Earth. So how about we look at that, but let's try comparing a molecule like N2, for example, with something much more lighter, like, say, diatomic hydrogen. What would we get? Well, we just need to plug those varying masses into our formula. So let's say we did that. What would we get? Try making a guess in your head right now. All right, so let's see how we can apply this to real life, right? We know the masses and we have this real world data right now of how all these atoms essentially perform on the weighing scale. And let's try using this in a very similar way that we did to the escape velocity example, where we used real world data to get a surprisingly accurate answer, actually, of Earth's escape velocity. So we already know our formula here, but let's set some ground rules first. If we revisit our formula back here, 3 and R stay the same. Temperature, we need to figure out, just a realistic temperature for Earth. And studies show that this is around T is equal to 15 degrees Celsius if you look at the Earth as a whole, right? I have no idea what that is in Fahrenheit. I'm sorry for anyone that's living in the United States. 15 degrees Celsius, if you look at all the temperatures on Earth, right? As you can see, it's leaning more towards the coal side. There, of course, are some really hot places on Earth, but that tends to get canceled out and we lean towards this. And that actually, though, is not what we need for our formula. We need temperature in Kelvin for this to work. And the conversion is really easy. Just add 273 degrees to that and get 288 Kelvin. Hopefully you understand the math, but you don't really need to understand the math even in this case, because as long as it makes sense, hopefully we can get somewhere. So let's try plugging everything in now that we have a ground rule that the temperature is going to stay 288 degrees Kelvin, right? But between all the gases we look at, just so we can compare things effectively. Vmol square root 3 R, as I said, is 8,314. It related, energy to number of atoms to temperature. I'm not going to write down all the units. This is a good formula. So let's just trust that all of the things are going to cancel out and we're going to be left with a clean answer. So we have 288 degrees Kelvin. Remember, this is 3 times R times T, and then we divide that by M, and then in this case, molecular mass is actually 2. Very simple stuff, right? And we're not doing anything super complicated. Multiplication, division, square rooting. You can plug this in on your calculator now, and I trust that you'll get the same answer as me. I rounded mine slightly, but you should get something at least close to this in this ballpark. 1900 meters per second. Now, let me remind you what this means, all right? A diatomic hydrogen atom at 15 degrees Celsius, we can expect it to be moving around at 1900 meters per second. That is more fast than you could ever imagine, faster than a plane, faster than sound. This is crazy, right? This is like almost 2 kilometers a second. That's how fast hydrogen atoms move. That's mainly because they're light, okay? But I don't think we have anything to compare this with yet. So let's try comparing this with nitrogen. That's like the biggest constituent of our atmosphere, at least on Earth. V mole, again, is equal to, maybe you can try doing this in your head, 3 times 8,314 times 288. Wow, this is really messy. But hopefully you can still get the idea that all of this top stuff stays the same, but this bottom thing changes. I mean, as you can expect, this whole top part's being divided here. So of course you're going to expect a smaller answer. It's about 560 meters per second. Like I rounded quite a bit of it off, so it might be different for you, but that's the sort of number you get, okay? And this also is faster than the speed of sound, which is closer to 300 meters per second, all right? And at first, it might not make any sense that atoms can move faster than the speed of sound. Like these guys are flying around from place to place like you wouldn't even know, all right? There's a bunch hitting you right now, and you don't notice it, of course, because they have low mass and low momentum. But like this is what atoms are doing. If only you could see them, you'd see how fast they move around. But again, you're probably wondering why these things move faster than the speed of sound. Well, it'll make sense if you realize that these atoms make up air, and air also carries sound. So at the very minimum, it has to travel at the speed of sound, and these guys travel a bit faster because they gotta, carry sound a bit further than they need to. So that's kind of what we have for speed. But how does this all relate? So where does this leave us with everything, right? We've learned escape velocity. I'm using some shorthand. Hopefully that works. We also know about molecular velocity. But neither of those alone are the whole picture, and we can't understand atmospheric retention if we only know one of these, or even if we know both, in fact. What we need to know, what's more important than everything else, is the relationship between these two factors. And why is it important? Well, it's important because the entire concept of an atmosphere is a layer of gas that's held over a planet with its gravitational field. The gravitational field part is this escape velocity. The layer of gas part is this molecular velocity part. And depending on how fast molecules move versus how fast they need to be to escape into space, that plays a huge role in how our atmosphere is developed. Specifically, if we looked at Earth, you can take the solid circle as the planet, of course, and this dashed one as the atmosphere, which, well, debates vary because there's really no definition as to where the atmosphere truly ends, but let's say it's about 100 kilometers just to be safe. All right, cool. So this is Earth. And what we need to figure out is, let's say if we zoomed into this, if we zoomed into this, and what would we see? We'd see all these atoms, all right, of a gas, and this is the boundary we see, just like usual. Well, where can an atom or a molecule be moving, right? Because atoms and molecules follow what we call Brownian motion, which means they move essentially in random directions by bouncing off of each other. So they can be moving anywhere, right? Away from Earth, straight up, really anywhere, right? The thing we've seen with escape velocity, though, is escape velocity, this number that we quantified earlier, which was 11,000 meters per second, which is a huge number, by the way. Even that, even if you're going at 11,000 meters per second, that can only apply. That can only apply when you're moving directly away from Earth. If you're moving, for example, closer to Earth, like this atom, that doesn't do anything for you. You're not going to go to space with that. Assuming this is random motion, though, there is going to be a quantity of atoms that are going to be moving directly away from Earth, right? And in that case, when you're looking at those atoms, right, if their speed, their molecular velocity, if mv is greater than or maybe even equal to escape velocity, then they'll escape, okay? They'll escape. And when they escape, you know there's no atmospheric retention going on. No retention. Retention is gone if they end up escaping, right? And they'll only end up escaping if their molecular velocity is greater than or equal to their escape velocity. Well, what did we see earlier? All right, what did we see earlier? We saw earlier with real examples was H2 had a molecular velocity of roughly 1900 meters per second. And clearly that's lower than 11,000 meters per second. So why is hydrogen not part of our atmosphere? Like hydrogen is not even present at all. Like you wouldn't be able to find it in our atmosphere. Why? Right? Why is hydrogen not present, but nitrogen, diatomic nitrogen, with roughly 500 meters per second in terms of molecular speed, how come nitrogen survives and it's in fact 72% of our ATM, our atmosphere? So why is this going on? It's really confusing, isn't it? Ideally, it should be exactly like I said. If the molecular velocity is greater than or equal to the escape velocity, there's going to be no retention of that specific molecular atom. And likewise, if the molecular velocity is less than or equal to the escape velocity, then you should have retention. That's not how it works, actually. And why? Well, because molecular velocity is an average. And man, average is a killer word because if you have this closed contained system, there's going to be atoms moving in all different directions and all different speeds. If you look at this, I've drawn this in more or less vector format. There's direction, so the arrow's angle represents, of course, where the atom's going, and the longer the arrow, the faster they're moving, right? So some atoms can move slowly, right? Even if the temperature and everything is the same, and ideally they should all be moving at the same speed, they don't, all right? That's the problem with atoms. But if you take enough atoms in a group, right, and they're all assumably in the same condition, you will eventually see that if you take the sum of all their speeds and you divide them by the number of atoms, again, this is just this is literally just a mathematical mean. Like, this is what you've learned in grade 5, 6 maybe. If you take that, it'll eventually approach its mathematical molecular velocity, right? And so for H2, if you look at enough H2s, that'll be 19,000 meters per second. Some might move at 10 meters per second. That might be an exaggeration. Some might move much slower. Some might move much faster. But this is what they gravitate towards. All right. And here's the thing. This isn't constant either. So like an H2 molecule that's moving slow right now, slower than it should be, it might be moving much faster than the average at one point. And over time, you'll assume that every atom has been near the lowest end of the speed spectrum and at the highest end of the speed spectrum. So when molecular velocity is roughly equal to escape velocity, and by that I mean when a molecule's speed approaches the speed that you need to escape the atmosphere, you're actually not in a good situation when it comes to retention. Because assuming your molecule is moving directly away from the Earth and it's moving faster than its average speed, which is actually really plausible, over time, you'll eventually lose all of those atoms and molecules from your atmosphere, whatever you're looking at, right? What we're looking at is long-term retention, right? If you have this situation going on where molecular velocity is roughly equal to escape velocity, you won't have long-term retention. It'll be a matter of minutes and things will equalize and all your substance will essentially dissipate into the vacuum of space, right? What we need is a really huge gap, in fact, a gap that you might not even be able to comprehend. And this gap, my friends, this gap is really this. That might have been a mind blaster because, I mean, of course, this is much more intuitive. Where was I? Over here. This whole concept of molecular velocity being greater than or equal to escape velocity. I mean, it's simple on paper, but that's not how things work in real life, as you can see, right? Because H2 and N2, they both have a velocity that's lower than, well, Earth's at least escape velocity. And yet one of them ends up being retained and the other one doesn't, right? And this is exactly why we have this distinction and why we have this extra little rule that allows us to filter certain gases for retention capabilities better. So, as I said, molecular velocities are averages, and at a huge scale, atoms and molecules, they can move much faster or slower, but the average tends to approach the molecular velocity we calculate mathematically, right? The problem is this isn't constant. Some atoms move faster and slower, right? And over time, slow atoms will eventually get to the fast end of the spectrum, and eventually it's almost 100% likely that your atoms will have crossed the escape velocity and will be moving completely away from the Earth, and your elements will dissipate, and you won't have an atmosphere made of that substance anymore, at least over the long term. That's why we have this really huge difference that we need to talk about right now. So what we've seen scientifically is that for an atmosphere to be retained, at least for a certain gaseous element, the molecular velocity of that gaseous element needs to be at least 10 times slower. Or another way of seeing it is the escape velocity needs to be 10 times greater than that gas's molecular velocity so it can be retained inside. That's an order of magnitude higher, right? It's not just like they need to be equal or close to equal. No, this is huge, right? And this ensures, the reason it's such a large number, like 10, is that we're assuming that it's a probability game. As I said earlier, it's an average. Things can go faster or slower. And over time, it's almost guaranteed that some of your atoms will move fast enough and in the right direction to leave. And if you don't have such a high escape velocity, they'll do that if it's maybe 8 times the molecular velocity or 7 times. In a few thousand years, your atmosphere, let's say made of some hypothetical substance, it'll dissipate. So for any long-term retention of the atmosphere, it needs to be around 10 times the molecular velocity. And this is exactly why we have the situation we see today. EV is greater than or equal to 10 MV. Escape velocity needs to be greater than or equal to 10 times an atom or molecule's molecular velocity for there to be chances of it retaining in the atmosphere. Okay, well, that's pretty crazy. There's a huge difference that needs to be at least present for these things to happen, at least in terms of atmospheric retention. What does this leave us with when we look at hydrogen and diatomic nitrogen? Well, H2 was a crazy speed, right? It was crazy. 1900 meters per second. All right. Now, of course, 1900 meters per second is lower than the escape velocity for Earth. But here's the thing. It's not the molecular velocity that needs to be lower than the escape velocity. It's 10 times the molecular velocity. So this is times 10. And that ends up giving us 19,000 meters per second. And that's actually greater. All right. That's greater than, it's not greater than or equal to, sorry. It's greater than our escape velocity of 10,000 meters per second. And that, my friends, is the reason why H2, diatomic hydrogen, does not retain in our atmosphere. Does not retain. How cool is that? Come on. Come on. Don't tell me that that didn't blow your mind. All right? Let me blow your mind even more. The reason why nitrogen actually ends up staying in our atmosphere, and by the way, hydrogen is the most abundant element on the Earth. And because of this simple math, even though it's the most abundant element in the universal level, it's not part of our atmosphere. And this is why that's the case, right? And then N2 is closer to 500 meters per second. Times that by 10, but you get a much lower number. 5,000 meters per second, and that is less than the escape velocity. And this is 10 times the molecular velocity. That's less than the escape velocity, and it's because of that that nitrogen does retain. And that's also the reason oxygen retains too. And all the other elements that make up Earth's atmosphere specifically. But if you've been observant, you can see that this doesn't just have to apply for the Earth, right? This is any celestial body. We're looking at a formula like 2GR. This could be anything, as long as you know the gravitational constant and you know the radius. What else do you need? You could do this for the moon. And if you do this for the moon, you realize that the moon just doesn't have enough gravity to host any of these things. It's not a matter of, well, how fast any of these elements move. It's just that the moon has a really low escape velocity and these things just fly off into space. And that's sad for the moon. But let's look at another planet that might be really interesting, Venus. Venus, I mean, we've been talking about, climate change on Earth for a long time, but Venus is like the master of climate change. Like, if we had the type of climate change that Venus has, like, we'd be very, very dead. All right. That's because Venus's atmosphere is 96.5% CO2. CO2, that's the stuff that we're releasing into our atmosphere right now. Well, why does Venus's atmosphere have so much CO2? Think about it like this. At least this is one of the reasons. We can mathematically explain this, at least looking at what I've explained so far here. Venus is about the same size as Earth. So this is Venus, this is Earth. It's maybe about 10% smaller, actually. So why? I mean, they have the same, I mean, relatively the same gravitational constants, and they have relatively the same radius. So what's going on? Why is there so much CO2? And by the way, CO2 is heavier than all of the things I've described. It's heavier than N2. It's heavier than O2. So why does a heavier element stick to Venus and not Earth? Well, partially because Venus is hotter than Earth, right? Because it's closer to the sun. And what does heat do? Heat makes atoms move faster. And what does that do? It increases their molecular velocity, right? And so if N2 might have been able to survive on Earth because it was moving slower at 15 degrees Celsius, by the way, it won't be able to do that on Venus at, hundreds of degrees Celsius. Hundreds of degrees Celsius. It won't be able to do that. And by the way, the definition of temperature is how fast atoms move, right? You go from water to a gas, and gas is just faster moving water atoms, right? That's why you can see patterns like this when you start understanding the very basic physical properties that make things up. And this is exactly why CO2, a heavier atom, is actually able to stay, right? Because now 10 MV for CO2 is still less than or equal to escape velocity. Kind of get that now? You can apply this for literally anything you see around you. I hope everything makes a lot more sense. I know I've gone way over time right now, so let me just leave it off to that. Hopefully now you know the secrets of the universe a bit more, and hopefully you saw the same sort of awe that I had when I learned this too. So that's me. That was master class-ish with Aaryan. See ya. Well, now